Hello and welcome to this new chapter on heat engines. We'll start this chapter by introducing the air standard cycle. But before explaining what is the air standard cycle, we should know that in an internal combustion engine, energy is provided, of course, by burning fuel within the combustion chamber. So because of combustion, the working fluid will change its composition from air and fuel to combustion products during the cycle. However, since air is dominantly composed of nitrogen, so we say air is 79% nitrogen and 21% oxygen, and nitrogen will hardly participate in any chemical reaction. So for this reason, the working fluid will resemble air all the time during the cycle. So saying that the working fluid is air all the time during the cycle is a valid assumption and will greatly simplify the analysis of engines. So this is the main assumption of the air standard cycle. So in the air standard cycle, the working fluid is air all the time during the cycle. But why we want to use the air standard cycle in the analysis of engines and not the actual analysis of engines? Because the actual analysis of engines is very complicated for several reasons. The first reason, as we said, the working fluid will undergo combustion. So as a result, it will change its composition during the cycle, and also will undergo heat transfer and friction with the cylinder walls. So it will lose energy by heat transfer and by friction with the cylinder walls. Moreover, in actual engines, we deal with open systems. So in an open system, the mass of the working fluid will change during the cycle. So that's why we have the intake stroke and the exhaust stroke. So in the intake stroke, a fresh mass will mix with the residual gas from the previous cycle, and also in the exhaust stroke, the combustion products will be expelled to the surroundings and some residual gas will remain inside the cylinder. So as a result, we have an open system problem with the changing composition, which is a very difficult problem to analyze. So to make the analysis of engines more simplified, the real cycle is approximated as an air standard cycle. So what are the air standard assumptions used in the analysis of air standard cycles? The first assumption is that the working fluid is air. So as we said, air is dominantly composed by nitrogen, and nitrogen will hardly participate in the combustion reaction. So for this reason, the working fluid will resemble air all the time during the cycle. Now the working fluid will circulate in a closed loop and always behave as an ideal gas. So in an air standard cycle, we deal with the closed systems. So unlike the actual engine where we deal with open systems, in an air standard cycle we deal with the closed systems, and in the closed systems the mass of air is constant and no exchange of mass between the system and the surrounding. So to maintain a constant mass of air, of course, we need to eliminate the intake and exhaust strokes. So the intake and exhaust strokes are not considered in an air standard cycle. So that's why we have a constant mass in an air standard cycle. Now the second assumption, all the processes that make up the cycle are internally reversible. So what do we mean by internally reversible? We mean that no losses are present, of course, due to friction, so by friction and heat transfer. So no losses are present by friction and heat transfer between the working fluid and the cylinder walls. So in this case, we deal with ideal processes. The third assumption is the combustion process is replaced by a heat addition process from an external source. So as we said, the combustion process will change the composition of the working fluid and it will complicate the analysis. So to simplify the analysis, we will replace the combustion process by a heat addition process. So imagine we have an external source surrounding the air. So this external source is at a higher temperature. So as a result, it will supply heat to the air. Now, the last assumption, the exhaust process is replaced by a heat rejection process that restores the working fluid to its initial state. So since we don't have an exhaust stroke, we will replace the exhaust stroke by a heat rejection process. So now, in the heat rejection, imagine we have an external heat sink surrounding the air. Of course, this heat sink is at a lower temperature than air, and as a result, heat will be rejected from air to the heat sink, and this will replace the exhaust stroke in the air standard cycle. Now, the heat rejection process, of course, will restore the working fluid to its initial state, to state 1, and in order to repeat the cycle again. Now, an additional assumption that can be used is called the cold air standard assumption. So in this assumption, air is assumed to have constant specific heats. So we know that air during the cycle will change its temperature. And we know that the specific heat at constant pressure is temperature dependent, and the specific heat at constant volume is temperature dependent for an ideal gas. However, in the cold air standard assumption, these specific heats are assumed to be constant. So Cp is constant and Cv is constant during the cold air standard assumption. Now, any cycle where the air standard assumptions are applicable is called an air standard cycle. And in the next video, we will consider the first air standard cycle called the constant volume heat addition cycle, or the Otto cycle. So see you in the next video.